Now let's look at what Newton did with his universal theory of gravity. There was much dispute at the time among people like Robert Hooke, Christopher Wren, and Edmund Halley about the force of gravity. They didn't even really think of it as a force in these times. That word hadn't been coined yet. But how the influence of gravity fell off with distance. In other words, what was the power in the force law 1 over r to the n? Did it fall off linearly with the distance, or is the inverse square? It was intuitive that it might be an inverse square law, since light falls off similarly. When you double the distance from a light source, the intensity through any point goes down by a factor of 4. Treble it, it goes down by a factor of 9. And people thought, physicists thought, that that force law might apply to gravity as well. But they didn't know and they couldn't prove it. Newton knew about Huygens' centrifugal force, and he argued that for a planet to be held in its orbit by gravitational acceleration, then if the exponent in the force law was 2, an inverse square law, you would automatically get Kepler's third law, and he'd proved this. Would the same attractive force affect terrestrial objects? He needed to develop some techniques to sum up the force from the Earth on, for example, an apple or a tree or a person standing on its surface. He did a geometric proof which used his elements of calculus to show that when you were standing on a large object like the Earth that was symmetric in a sphere, that the force acts as if all the mass was concentrated from a point at the center. He also proved that spherical shells outside would cancel and only interior mass counts. Using a recent determination from his time of the size of the Earth, Newton compared the force on an apple to the moon. And he showed that the apple's force that gives it its weight on the Earth's surface does indeed behave the same way as the force on the moon at a much larger distance with a much larger mass, and that these objects are behaving according to the same force law, and that it is an inverse square law. This is a remarkable insight, and it leads him to his universal law of gravitation, which we see here in the equation form. The force between any two objects is equal to a physical constant, the gravitational constant, times the product of the mass of the two objects divided by the square of the distance between them. So if you double the mass of either object, the force doubles. If you double the mass of both of them, it goes up by a factor of 4. It's independently scaling with each of the masses, and by the inverse square of the distance between them. The distance gets 2 times smaller, the force gets 4 times larger. The distance gets 2 times larger, the force gets 4 times smaller, and so on. Newton's theory is only exact in the artificial case of two objects. In almost every realistic astronomical situation, there are more than two objects, for example, the Earth, the Moon, and the Sun, and in that case, it's only an approximation, and you would actually need a computer or extended calculation to solve for the gravity forces. He also imagined that acceleration by gravity is what gives things their weight. And so he imagined that you could be in a situation of an elevator moving at a constant speed and you would feel your normal weight due to the gravitational force on you. If that elevator was accelerating upward, you'd feel an increased weight because the acceleration of the elevator would contribute a force on you that adds to the force of the Earth. If the elevator was accelerating downwards, you would feel less weight because the force from the elevator was subtracting from the weight caused by the gravity of the Earth. And in the unfortunate situation that the cable broke and the elevator went into free fall, you would feel no weight because both you and the elevator would be free falling under the force of gravity with no resistance. His theory also explained the tides. If the Earth didn't rotate, the tidal bulges would be oriented along the Earth-Moon line. But because the Earth is rotating, they tend to lag slightly ahead of the Earth-Moon line. The reason why there are 2 tides a day is because the Moon pulls on the Earth, and it pulls a slightly stronger amount on the near side of the Earth than the far side of the Earth. So it pulls the ocean upwards on the side towards it, but it also stretches the Earth. And it's this stretching force in both directions that leads to 2 tides per day. This was a clever insight of Newton's and showed that his work had practical benefits as well. These ideas also lead to the idea of gravitational potential, where the mass of an object gives you a visual of a deep potential well, which you need energy to climb out of. We see here a graphic showing the gravity potentials of the planets in the solar system, some of these, of course, not known in Newton's time, indicating that the relative mass gives much shallower and deeper potential wells according to the gravity. Gravity simply scales by mass for a planet or a moon. He also realized that you could get an object to a speed launched from the surface of the Earth where it might escape the gravity forever. Toss the apple into the air, it will return into your hand. But he imagined you could toss it at a speed that was high enough that the acceleration would take it to the point where it left the Earth's gravity forever. In fact, he imagined a speed where, in a transverse sense, it would go into an orbit, and 40% more than that transverse speed, it would leave the gravity forever. This is a thought experiment that leads to the idea of an orbit. And in fact, the math works out. Gravity means the moon is constantly falling towards the Earth, just as the apple is. Its transverse motion is what creates the orbit, but at every point it's accelerating down towards the Earth. And that acceleration is the same as the acceleration of the apple at a much smaller distance. The gravity force is operating in exactly the same way. On the right, we see a thought experiment he did, where he imagined firing a cannonball from the top of a high mountain. At some speed, he realized the Earth would fall away at the same rate as the cannonball is falling towards the Earth. And at that point, its distance from the Earth's surface never goes down. He's created an orbit. Now, he was hundreds of years away from a time when the technology would exist to fire any cannonball or any object that fast. But this is conceiving of space travel and orbits hundreds of years before space travel actually happened. And so we can think of gravity, even when we walk, as if we're walking and falling at the same time. Let's hear this from Laurie Anderson.
You're walking, and you don't always realize it, but you're always falling. With each step, you fall forward slightly, and then catch yourself from falling. Over and over, you're falling, and then catching yourself from falling. And this is how you can be walking and falling at the same time.
Newton's theory was stunningly confirmed when he made the prediction of the return of Halley's comet. Asked about action at a distance, this mysterious gravity force that operated across the vacuum of space without any visible strings, he said, "I frame no hypothesis." In other words, he didn't know. But with his equation, he'd united the motions of terrestrial and celestial objects with a single, simple equation. There were other people that were influential in the time in this community of intellectuals in London. Two in particular are important in encouraging Newton's science. Christopher Wren was a mathematician, an astronomer, and a physicist. He was a civilian professor at Oxford and a member of Gresham College. Most people know him as an architect. After the fire of London, he was in charge of rebuilding 52 churches. He's buried in St. Paul's Cathedral, and on his gravestone it says, "If you seek a monument, look around." Another important figure was Edmund Halley. Halley, of course, is known to us from his comet, but he was a remarkable polymath. He observed in St. Helena to catalog the southern sky. He observed a transit of Mercury and explained trade winds and monsoons. He met Newton many times while exploring the nature of elliptical orbits. He was an inventor who invented the diving bell and a special form of a compass that was much better during sea voyages. He captained his own ship while using magnetic declination for finding latitudes at sea, and he pioneered statistics in the use of actuarial tables. He was the Astronomer Royal for England, and of course a comet enthusiast who realized that Halley's comet was periodic. Most importantly for this part of the chronology, he convinced Newton to publish his results, because Newton was in no hurry to publish at all. For Newton it was enough that he knew it. He didn't care if anyone else knew the result. So Halley put up the money to pay for the publication of Newton's work. And that work was the Principia, one of the greatest books in the history of science, from 1687, Mathematical Principles of Natural Philosophy. This encyclopedia is his work in physics, with the basic laws of motion, demolishing the Cartesian system, and applying the simple laws of physics and gravity to the world. This is a foundational text of modern physics and astronomy. In the mid-20th century, the great physicist Subrahmanyan Chandrasekhar, who won a Nobel Prize for his work on gravity theory, took a decade to go back and look at the work of Newton in Principia and see whether with modern mathematical methods he could improve on the work. He decided after years of study that he couldn't, that Newton had done the best possible job he could with this physics and mathematics, an extraordinary testament to his achievement. And that's the end of this topic.